A massive metal cylinder weighs over 500 tons. It stands as tall as a 30-story building. It is filled with thousands of gallons of explosive fuel. Engines ignite at its base. Flames shoot downward. Smoke billows in every direction. Then, slowly at first, then faster and faster, the entire structure lifts off the ground. It rises through the clouds. It pierces the edge of our atmosphere. And within minutes, it is traveling at 25,000 miles per hour. How does something so heavy go so fast? What force pushes it upward? The answer is surprisingly simple, and you can see it for yourself with a balloon. Let us get into the story of how a rocket reaches space, who figured out the physics behind it, and why escaping Earth is one of the hardest things humans have ever achieved. The story begins with a man named Isaac Newton. In 1687, Newton published a book called Philosophiae Naturalis Principia Mathematica, or the Mathematical Principles of Natural Philosophy. In this book, he laid out 3 laws of motion that changed physics forever. The third law is the one that matters for rockets. It states, for every action, there is an equal and opposite reaction. This sounds abstract, but it is actually something you experience every day. When you sit on a chair, your body pushes down on the chair. The chair pushes back up on you with equal force. That is why you do not fall through. When you swim, your hands push water backward. The water pushes you forward. That is why you move. When you walk, your foot pushes the ground backward. The ground pushes you forward. That is why you walk. A rocket works the same way. But instead of pushing against a chair or water or ground, the rocket pushes against its own exhaust. The engine burns fuel. The burning fuel creates hot, high-pressure gas. That gas shoots out of the nozzle at the bottom of the rocket at tremendous speed. The gas rushing downward is the action. The rocket moving upward is the equal and opposite reaction. A simple experiment proves this. Take a balloon. Fill it with air. Do not tie it. Let it go. The air rushes out of the open end in one direction. The balloon shoots off in the opposite direction. That is Newton's third law in action. The air escaping is the action. The balloon's movement is the reaction. A rocket is just a very powerful, very controlled version of that balloon. The air inside a balloon is under pressure. When you release it, the pressure pushes the air out. The same principle applies to rockets, except the air is hot gas produced by burning fuel. NASA explains that the force of the gas escaping is the action. The movement of the rocket forward is the reaction. Now, understanding why a rocket moves is one thing, but understanding how it escapes Earth's gravity is another. Gravity is the force that pulls everything toward the center of the Earth. It is what keeps you on the ground. It is what makes things fall when you drop them. And it is what makes launching a rocket so difficult. A rocket scientist named Benjamin L. Emerson from the Georgia Institute of Technology explains it this way. The rocket has to make thrust by burning propellant to create hot gases. Then it shoots those hot gases out of a nozzle. That is the action. The reaction pushes the rocket upward. The rocket must generate enough thrust to overcome its own weight. The weight of the rocket is the force of gravity pulling it down. Thrust is the force of the engine pushing it up. If thrust is greater than weight, the rocket lifts off. If thrust is equal to weight, the rocket hovers. If thrust is less than weight, the rocket stays on the ground. But lifting off is only the beginning. To reach space, the rocket must keep accelerating. And to stay in space, it must reach a very specific speed. That speed is called escape velocity. It is approximately 25,020 miles per hour, or about 40,000 kilometers per hour. Why so fast? Because Earth's gravity extends far into space. It does not stop at the atmosphere. Even at the altitude of the International Space Station, which is about 250 miles above Earth, gravity is still about 90% as strong as it is on the ground. Astronauts float not because there is no gravity, but because they are in free fall, constantly falling around the Earth. To escape Earth's gravity forever, the rocket must go fast enough that its forward momentum is stronger than the gravity pulling it back. It is like riding a bicycle up a hill. If you build up enough speed at the bottom, you can coast to the top without pedaling. If you do not have enough speed, you stop and roll backward. The rocket is the same. At 25,000 miles per hour, the rocket can coast away from Earth forever. At any slower speed, it will eventually fall back or go into orbit. Different planets have different escape velocities. Jupiter is the most massive planet in our solar system. It could swallow 1,000 Earths. Its escape velocity is 133,100 miles per hour, more than 5 times Earth's. A black hole is so massive that its escape velocity is higher than the speed of light, which is about 670 million miles per hour. That is why even light cannot escape a black hole. To achieve these incredible speeds, rockets must be extremely powerful and extremely efficient. But there is a problem. The rocket cannot carry enough fuel to keep its engines burning all the way to space. The more fuel you add, the heavier the rocket becomes. The heavier the rocket becomes, the more fuel you need to lift it. This is called the rocket problem, and it has a clever solution. The solution is staging. Staging means building a rocket in multiple sections, or stages, stacked on top of each other. The first stage is the largest. It fires at launch and provides the initial thrust to lift the rocket off the ground. When its fuel is exhausted, the first stage separates and falls away. The second stage then fires, now pushing a much lighter rocket because the heavy first stage is gone. This process repeats for as many stages as the rocket has. The Saturn V rocket that carried astronauts to the moon in 1969 had 3 stages. The first stage lifted the rocket off the ground. It burned for about 2.5 minutes. Then it separated. The second stage fired next, pushing the rocket higher and faster. Then it separated. The third stage fired to push the rocket all the way to orbit and then toward the moon. Staging solves the weight problem. By discarding empty fuel tanks and engines as they are used, the rocket becomes lighter and can accelerate more easily. Without staging, reaching orbit would be nearly impossible. There are different ways to stage rockets. Serial staging, used on the Saturn V, places smaller stages on top of larger ones. The top stage fires only after the bottom stage is empty and discarded. Parallel staging, used on the space shuttle, attaches smaller booster rockets to the sides of a central core. All engines fire at launch, but the strap-on boosters are discarded when empty while the core continues burning. Some rockets use both methods. The Titan III, for example, had a liquid-fueled core with 2 solid rocket boosters strapped to its sides. The boosters fired at launch and were discarded first. Then the first stage of the core burned and was discarded. Then the second stage fired to carry the payload to orbit. The physics behind rockets has been understood for centuries. But turning that understanding into a working machine took decades of trial, error, and genius. The technology of rocket propulsion first appeared in Asia between 1200 and 1300 AD. Early rockets used black powder, a mixture of saltpeter, sulfur, and charcoal. These rockets were used primarily as weapons, especially during the early 1800s with the Congreve rockets developed by British officer William Congreve. But their performance was poor. They were inaccurate and unreliable. By 1815, military use of rockets had declined. The idea of using rockets for space travel grew in public interest between 1880 and 1930. 3 pioneers stand out. The first was Konstantin Tsiolkovsky, a Russian schoolteacher. In 1898, he proposed the idea of space exploration by rocket. In 1903, he published a report titled Exploration of the Universe with Rocket-Propelled Vehicles. In it, he suggested the use of liquid propellants for rockets to achieve greater range. He also stated that the speed of a rocket was limited only by the exhaust velocity of its escaping gases. For his vision and careful research, Tsiolkovsky has been called the father of modern astronautics. The second pioneer was Robert H. Goddard, an American. Goddard conducted practical experiments in rocketry. He was interested in reaching higher altitudes than balloons could achieve. In 1919, he published a pamphlet called A Method of Reaching Extreme Altitudes. His earliest experiments were with solid propellant rockets, but he soon became convinced that liquid fuel would be much more efficient. No one had ever built a successful liquid propellant rocket before. Doing so was much more difficult. Fuel and oxygen tanks, turbines, and combustion chambers all had to be designed from scratch. But Goddard persevered. On March 16, 1926, he achieved the first successful flight of a liquid propellant rocket. Fueled by liquid oxygen and gasoline, the rocket flew for only 2.5 seconds. It climbed just 12.5 meters, or about 41 feet. It landed 56 meters away in a cabbage patch. By today's standards, that flight was unimpressive. But it was the rocket equivalent of the Wright brothers' first flight at Kitty Hawk. Goddard's experiments continued for many years. His rockets became bigger and flew higher. He developed a gyroscope system for flight control and parachute recovery systems. He has been called the father of modern rocketry. The third pioneer was Hermann Oberth of Germany. In 1923, he published a book called The Rocket into Interplanetary Space. His book became the handbook for amateur rocketeers. Small rocket societies sprang up around the world. In Germany, one such society led to the development of the V-2 rocket, which was used against London during World War II. Oberth's work inspired Wernher von Braun and other German engineers. For his achievements, Oberth has been called the father of spaceflight. The V-2 rocket was small by modern standards. It burned a mixture of liquid oxygen and alcohol. It could carry a 1-ton warhead to a height of 50 miles and a range of hundreds of miles. It was the most advanced rocket of its time. After World War II, German rocket scientists came to the United States and the Soviet Union, bringing their knowledge with them. The American space program was built on the foundation they helped create. A modern rocket launch is a carefully choreographed sequence of events. Every second is planned. Every milestone is monitored. Approximately 38 minutes before liftoff, the SpaceX launch director gives a go for propellant loading. 35 minutes before launch, RP-1, which is rocket-grade kerosene, begins flowing into the rocket. Liquid oxygen loading begins at the same time. 16 minutes before launch, the second stage begins loading its liquid oxygen. 7 minutes before launch, the Falcon 9 rocket begins chilling its engines before ignition. 1 minute before launch, the flight computer begins final pre-launch checks. The propellant tanks are pressurized to flight pressure. 45 seconds before launch, the launch director gives the final go for launch. 3 seconds before launch, the engine controller commands the ignition sequence to start. At T-0, the rocket lifts off. 7 seconds later, it clears the launch tower. 1 minute and 8 seconds after launch, the rocket experiences max Q. This is the moment of peak mechanical stress on the rocket. The combination of speed and atmospheric pressure puts maximum strain on the structure. Rockets are designed specifically to survive max Q. 2 minutes and 16 seconds after launch, the first stage engines cut off. 4 seconds later, the first and second stages separate. The second stage engine starts almost immediately. The first stage, now empty, begins its descent back to Earth. Approximately 7 minutes and 54 seconds after launch, the first stage lands, either on a drone ship at sea or back at the launch site. Meanwhile, the second stage continues climbing. About 8 minutes and 16 seconds after launch, its engine cuts off for the first time. The rocket is now in orbit. Later, the second stage may restart its engine for a second burn to reach a higher orbit before finally releasing its payload of satellites or spacecraft. All of this happens because of Newton's third law, a balloon with air, a fire extinguisher on a spinning stool, a Saturn V carrying humans to the moon, a Falcon 9 delivering satellites to orbit. The physics is the same. Push gas down, go up. There is one more concept to understand. The fuel that a rocket burns is not just any fuel. It needs both fuel and an oxidizer. In the atmosphere, a car engine burns gasoline using oxygen from the air. But in space, there is no air. A rocket must carry its own oxygen. This is why rockets use liquid oxygen, or LOAX, as an oxidizer. The fuel is typically something like liquid hydrogen, methane, or RP1, which is refined kerosene. The fuel and oxidizer are pumped into the combustion chamber, where they ignite. The burning produces hot, high-pressure gas. That gas expands and is forced out through the nozzle. The gas rushing out creates the thrust that pushes the rocket forward. The amount of thrust depends on two things: the mass of gas being ejected and the speed at which it is ejected. More gas, faster gas, equals more thrust. This relationship is expressed in an equation. Thrust equals mass flow multiplied by velocity. The nozzle of a rocket engine is shaped specifically to accelerate the gas to supersonic speeds. The gas enters the nozzle at subsonic speed, passes through a narrow throat where it reaches the speed of sound, and then expands in a diverging cone, accelerating to many times the speed of sound before exiting. This is why rocket exhaust looks so dramatic. It is moving faster than the speed of sound. It is incredibly hot. It is the visible evidence of Newton's third law at work. So the next time you watch a rocket launch, remember the science behind it. The flame shooting downward is not wasted energy. It is the action. The rocket rising upward is the reaction. The engineers who designed it are using a principle that Isaac Newton wrote down in 1687. A balloon with air demonstrates it. A fire extinguisher on wheels demonstrates it. A 500-ton rocket lifting off the launch pad demonstrates it. Push gas down, go up. That is the simple secret behind humanity's greatest journeys into space. And that is how a rocket reaches space.